We are beginning our last session of the day, and our first speaker is Enrique Madeni, and he's going to talk about the imprint of global hierarchical cloud collapse on the cluster structure. Without further ado.
Okay. Well, hello, everyone. Right now, I cannot see anyone, but I hope you can see my presentation. It's a pleasure to do this. It's the first one for me, so I hope it all works out well. And so, like Paula said, I'm going to let you know some of the results that we've been obtaining lately about how the hierarchical structure in the parent cloud makes its imprint on the resulting cluster from this cloud. And here's the list of my collaborators here. Marina Kunkel is among them, and I understand that she is participating here in the conference. So how is the main physical mechanism that's behind everything I'm going to say is this idea of the global hierarchical collapse occurring in molecular clouds, as we have been advocating recently. And I'm just going to show you at one transparency summarizing how the scenario operates, so that then we can go ahead and look at how this scenario makes its imprint on the clusters. The first part is that solar neighborhood type clouds, precisely such as Orion, in principle must form by the reservoir of gas available in the galactic disk. And at these galactocentric radii, most of the volume is occupied by warm atomic or warm ionized hydrogen. But as it was shown, I don't know if you can see my pointer so that I can show it to point on the screen to you. As was shown maybe 20 years ago, motions in this warm medium generate, even they don't have to be strongly supersonic motions, just transonic motions are sufficient to non-linearly trigger phase transitions to the cold phase of the atomic gas. But when this happens, the density increases by about a factor of 100, the temperature drops by about the same factor, precisely because the pressure remains constant, and therefore the G's mass, which goes as the density to the -1/2 power times the temperature to the 3/2 power, drops precipitously by a factor of about 10 to the 4 due to the cooling and compression that happens simultaneously. And so the cloud quickly becomes G's unstable, and it begins to contract. Actually, this cloud may be like a collection of small cloudlets of small atomic clumps that are floating in the background warm gas. But then, as the cloud contracts, its mean density begins to increase, and then the average G's mass begins to decrease. And this is the idea behind Hoyle's gravitational fragmentation from almost 70 years ago. And therefore, as time proceeds, the G's mass is ever lower, and therefore the turbulent fluctuations present in the cloud can collapse at ever smaller masses. That is, the G's mass decreases, and then any density fluctuation that has a comparable mass can begin to go into collapse itself. And at the same time, the cloud gradually turns molecular, as has been advocated by several groups, because the column density is increasing, and so the cloud is self-shielding itself. Then, but as the collapse proceeds, then you have a larger and larger number of G's masses in the same cloud. Not only because the cloud mass may be increasing because of accretion from the background gas, but also because the G's mass is becoming smaller. When you have many, many G's masses, that means that the thermal pressure is essentially negligible, and then the collapse becomes filamentary, as it is well known for the case of, for example, the cosmological flow that produces a cosmic web. Therefore, what we have is a multi-scale collapse, in which small-scale collapses begin later and are happening within larger scale collapses. And this means that since everything is collapsing, all scales are accreting from their parent scales. with the filaments being the accretion flow from the cloud scale to the hub scale. And one thing that's very important then is that the small scale structures like the hubs have durations that are of the order of the freefall time of the parent structure because of the accretion. So this makes the hubs and the dense cores appear to have longer lifetimes than their own local freefall time. Then what are the implications of this? One of them is that the star formation accelerates in the contracting cloud. And this is because as the cloud becomes denser, a larger and larger fraction of its mass is at higher densities, and then they collapse on a faster timescale. Then eventually at some point, massive stars begin to appear because now the little clumps become more massive themselves, and then they can provide more mass to the stars that are forming. In our simulations, as I'm going to show in a few more minutes, the massive stars begin to appear when the star formation rate, local star formation rate, is on the order of 2 times 2,000 solar masses per mega year. But then when massive stars appear, then feedback appears and they begin to disperse the cloud. And so what happens to the star formation rate is that it first increases by contraction and then decreases again due to feedback. But before I go to the evolution of the star formation rate, let me just remind you, this is a result that I've mentioned at several conferences, so I'll be just quick, is that the filaments form. And they form because of large-scale accretion, right? So the filaments are not the result of strong turbulent shocks, they're the result of filamentary collapse. But then and in this plot here, for example, the plot in the middle, you have an image of the column density of a cloud in one of our simulations on a scale of about 25 parsecs from the top to the bottom. And the solid line indicates the longitudinal velocity of the gas along the filament. So in the bottom part, the velocity, here's the axis for the velocity. So the velocity is positive, it's going towards the central hub. And on the other side, it's also going to the central hub, and you have a large shock here. And this kind of velocity is seen if the filament is at some inclination, then you can see part of its longitudinal velocity as a velocity gradient along the filament, and it is very consistent with observations such as those of Alvaro in recent years. So now going to the cluster formation and structure, I would like to show you a simulation that we presented a long time ago, but actually it continues to surprise us as we dig deeper into it. The simulation is one of converging flows, just collisions of, you can think of them as turbulent collisions in the warm neutral gas in the galaxy. So the mean density is like a few particles per cubic centimeter. The box size is 256 parsecs. The maximum resolution is 0.06 parsecs. We have a realistic stellar IMF, and then we have feedback through a simplified implementation of radiative transfer. So this is the simulation. This is the whole box. The ruler here shows a scale of 160 parsecs. This is the simulation at a time of almost 19 million years after the simulation started. This is the structure that has formed from the collision of the streams with a little bit of turbulence superimposed on it, so that you fluctuations and you break the symmetries. And I would ask you to please keep your eyes looking at these two sites where two clusters appear, and we will call them cluster 1 and cluster 2. And you can see
1 minute.
Yes?
You have 1 minute.
Oh, already? Wow, okay, thank you. So this is the simulation, and you can see how a long filamentary cloud cluster forms, and we claim that this might be similar to Orion A. And then after some 20 million years, the cluster has formed massive stars that have managed to push the gas away. This is cluster 2. This is the little one. And as you can see, it forms, oh, sorry, let me go back. Now this is a scale of 15 parsecs. You can see how the cluster forms with in forming little groups that then, for example, these two groups are separated a distance of 2 parsecs. Then they merge. Then later on, more groups form in the filament, but at the same time, massive stars have formed that begin to destroy the fuel supply to the cluster, and so the remaining groups the closer ones manage to fall into the central hub, the other ones are just left there. And so what that means is that the cloud acquires a structure that is hierarchical itself. So it's a sort of self-similar. This is an image of the stars locations about 10 million years after the star formation started. And when you apply a friends of friends algorithm, with different values of the linking parameter, here's the linking parameter is short, and then the linking parameter is larger here. And you can see that at each value, you identify larger and larger groups, meaning that there's a sort of self-similar structure. Then the star formation rate increases by collapse first, and then decreases by feedback. And that means that the stellar age histograms peak at a certain age. This is a histogram 1.5 million years after the onset of star formation. All of the stars seem to be just less than 2 million years old. But then later on, because the star formation is accelerating, here are the stars that formed earlier. Now these are the stars that are forming right now, but the star formation rate is higher, so there's more of them. Later on, the feedback is beginning to destroy the supply, and now the stars are forming more slowly, and then you see a decrease, and so on and so forth. So histograms have a peak at the time of maximum star formation rate. And this is very consistent age histograms of embedded clusters, such as those of Pala and Stoller. More recently, we're working with Marina Kunkel on doing this with her very nice data from Orion. And so here are age histograms from the simulation. The green line is the histogram for the cluster, just raw from the simulation. The gray line is post-processed in the same way that Marina processes the observational data, and the pink line is actually the Orion D data, and you see a very nice correspondence in the age histograms. Since I don't have much time, I'll just say that this mechanism of infalling and acceleration of the star formation rate creates mass-age correlations and radial gradients. You can see basically that in an age radius histogram, at the center of the hub, there's stars of all ages, but at larger distances, there's a lack of young stars. And this is very consistent with recent findings, for example, by Kostas Getman and his team. Here's also a mass-age relation, mass versus age, and you see that there's like an upper envelope. And with Marina, we're now creating two-dimensional histograms of the population of stars, both in our simulation and in the Orion D data. And the black lines are the simulation, the red dots are the Orion data, and you can see that there's a qualitatively good agreement. This is just the population, the fact that, well, since I'm out of time, I'll skip on this, but this just shows how massive stars tend to form later. So this is a cumulative mass fraction as a function of mass for the stars. And you see that at the beginning, the mass distribution, mass histogram is bottom heavy, and then you build up the massive part of the stellar mass distribution. And with that, I finish, and I'll just leave up my conclusions, and I can take questions. Thank you very much.
Thank you, Enrique. So we have a couple of questions from our YouTube audience. Well, actually from audience in Leiden, starting with Alvaro, and he's asking, do clusters form in situ or do they grow over time in your simulation?
They grow over time. So the cluster, because the star formation rate is increasing at the beginning you have like a low mass type of cloud, but then over the course of a few million years, you begin to form more massive stars. So that means that there's both more massive stars and a larger number of stars. So the clusters are building up over a time span of about 5 million years or so.
Right, thank you. And another question from Yoni. And he asks that you noted that massive stars appear late. Is it the prediction of your scenario that GMCs should first form substantial low mass star populations and only then high mass stars?
Yes, exactly. Of course, you wouldn't look for them at the same place, right? But yet, it is totally correct that that would be the prediction. And so right now, one of my grad students is analyzing one of the evolution of one cluster in one of our simulations and comparing it to a low mass star forming cloud at the early times and a higher mass star forming cloud at later times in the simulation. And we are finding very good correlation. That again, the time between the low mass stage and the high mass stage is a few to several million years.
Thank you. And we could, of course, continue the discussion offline on the Google Groups forum. I will have a question for you there later on.
Perfect.
And so I'll thank you again for the very nice talk. And let's move on to our next speaker.
Thank you.
Thank you. So now we have Josh Eisner from the University of Arizona. And Josh will be talking to us about disk properties in the Orion Nebula cluster. Please go ahead.
All right, can you hear me?
Yep.
And see my screen? Okay, well, thank you for having me. This is a very interesting format for me. I really appreciate getting to do this from a comfortable chair and not having to go on an airplane to talk to you. So this is really cool. And what I'm going to talk to you today a little bit is the protoplanetary disk properties with really an eye towards planet formation potential in the Orion region in particular, and a little bit in general. And I think some of what I'll do in the introduction here is set the stage for the next couple talks to some extent also. So there are two main things I'm going to talk about in terms of disk properties and how they relate to planet properties. And those properties are mass, that's the main one, right? In astronomy, mass is kind of king of everything. The mass of the disk determines the mass budget for planet formation. The mass budget tells you what kind of planets you're going to form. And a useful benchmark is this old thing that Stu Weidenschilling came up with in the 70s, the minimum mass solar nebula, which is quite a simple construction, just saying how much mass do we need to form the planets that we see now. And that tells you you need something on the order of 100th to 1/10 of a solar mass. So you can use that benchmark, look at how much stuff is around stars in Orion, which is a typical star forming and planet forming region, and get some sense of the mass budget for planet formation in a typical case. There are more detailed questions you could ask, like what's the mass density, what's the gas density versus the solid density. Those things will affect details of planet formation, like is streaming instability possible? How do you have migration through the disk so that you can have solids accumulate in certain places? So the mass matters for that as well. And the other disk property that I'll be touching on is the size of disks and how that relates to the scale of planetary systems that can form. So that's sort of an obvious link. You look at the solar system, it's 30-ish AU. And so that's the scale of disks you're probably wanting to look at. Maybe you even want to look at smaller scales in disks. This is just a plot showing the NICE model, so one particular model of how the planetary configuration might have been more compact in the past when formation was happening. So you might have even needed a more compact mass distribution than we see today. And of course, this is just our solar system. If you look at extrasolar planets, of course, there are strong selection effects, but we know that there are many, many compact, massive extrasolar planetary systems. So there may need to be a lot of mass distributed in disks on pretty small scales. And so that drives you towards wanting really high angular resolution. So you can not just measure mass and mass density, but constrain the size on which you're measuring it so you can compare it to planetary system scales. All right. So here's a picture of Orion. You probably all know this. This is a conference about Orion, after all. And this is an infrared image from VLT Isaac. And I'm just going to overlay now an ALMA mosaic of submillimeter continuum emission on there. And these circles are highlighting positions where we detect some of those known stars in the submillimeter. And I circle them because this image has many, many pixels, approaching 1 billion pixels. It's kind of hard to see individual sources. But there are a number of detections. That triangle there is showing you the most massive star in the region, Theta 1 Ori C. So we can trace out not just disk properties, but how those properties depend on their proximity to the main ionization source in the region. And we also have some, you see, cloud emission from BNKL and from OMC1S that we have to deal with. And so this image is actually spatially filtered to try to get rid of some of that extended cloud emission and just focus on the compact protoplanetary disks. And I'll just say also for reference, the color coding is, I think red is just a known infrared cluster member, and blue are known optical HST identified proplids. All right, here's just zoom ins on a couple of those sources so you can see that these little dots in those images really are pretty much always resolved sources. Almost every source we detect is angularly resolved in these observations. And if we resolve the sources, we can measure their sizes, and so we can then measure the disk size distribution. And here is what that looks like. Here's just a histogram showing the disk size distribution in the region. You can see it's peaked 20 to 30 AU, and I'll just point out these are Gaussian half-width, half-max sizes with the beam deconvolved, so they should be kind of accurate Gaussian sizes if you think Gaussians are accurate. And there's just a benchmark what the size of the solar system is going out to 30, our current one, going back to sort of 15 with a more compact distribution we may have had in the past. And you can see that the distribution of disk sizes in the Orion Nebula cluster in the central region of the Orion Nebula is quite comparable to what we think the solar system looked like in the past and even what it looks like today. And then this plot is showing you how these sizes in the ONC compare to other regions that don't have these strong ionization sources and don't have the same high stellar density. So in particular, you can look at Taurus in the purple versus the ONC in red, and you can see the disk sizes are extremely different in the two regions. There are much bigger disks in Taurus than there are in the ONC, and that probably has something to do with environment, which I will return to momentarily. The other quantity of interest is the disk mass, right? We already talked about how that determines the mass budget for planet formation, so we really care a lot about that. And again, I've compared the ONC with other lower density star forming regions. And again, if you look at Taurus, the distributions are very different. Lupus, Chameleon, same situation. The only regions that are more similar to Orion are Sigma Ori and Upper SCO, which are thought to be significantly older than the ONC. So that may be disk evolution in the older sources versus environmental effects in Orion. All right, so let me just acknowledge that that last plot I showed you with disk masses is really just a measurement of flux with a simple conversion applied via this equation that assumes optically thin dust and a single temperature distribution of the material. So that would be what I've got labeled here as equation 1, 20 Kelvin in this plot. And just to show you how this equation might not give you the right answer, I put on here as well, using that simple equation with hotter dust, which you might expect in a region like the ONC where there's a strong heating source from the trapezium stars. And so that can change the derived masses you would get from a given measured flux. And then to be even more careful about it, we've run some radiative transfer models of disks of about this size and figured out how much mass gives you how much flux. And you can see that you can get errors in different parts of the parameter space. So at the higher disk temperatures here, we tend to get the wrong answer because we have assumed that it's a low dust temperature. The dust is still optically thin, but the temperature is wrong. If we go to high dust masses, that temperature effect gets more than offset by the optical depth effect. You can hide a lot of mass once the disk becomes optically thick, which does happen in the range of fluxes and masses that we're dealing with in Orion. So if we wanted to do this better, and this is something we haven't done yet, but we're in the process of doing in this region, we would do radiative transfer modeling for every source. Just to show you how that would work, this is some work from Nick Ballering, a former postdoc of mine, in Taurus, where we had well-sampled SEDs already done for us, and he went through and did radiative transfer modeling of every source, compared the disk masses from radiative transfer modeling to the analytic formula type ones, and typically the real ones, the radiative transfer ones, are a factor of 5 higher. So it does make a difference. A factor of 5 is a pretty big factor and helps to make those masses closer to what we want them to look like for planet formation. So we're going to extend this to the ONC soon. So I'll just now point out again, this is the disk mass distribution. That red curve there shows the minimum mass solar nebula value. And then this green curve shows maybe what you would get if you adjust this by doing real radiative transfer instead of just using that simple equation. So you actually start to move some of these measured masses into the part where they could form Jupiter-like planets, which is sort of interesting. And then there's a big problem actually with the assumption of the minimum mass solar nebula applied to this region, which is that it is based on a solar mass star, our star. The peak of the stellar mass distribution in the ONC is not solar mass stars, it's M stars. And so if you just assume that disk mass and stellar mass are correlated, you might say, oh, well, we actually need to move that back quite a bit because M stars are so much less massive. And if you start to put all these factors in, you may be measuring disk masses that suggest that most of these systems can form analogous systems to our own. So that's kind of an interesting finding, I think. All right, I promised to return to this idea of environment, so that's what I will do for the conclusion of the talk here. The main environmental effect in the ONC that we expect is photoevaporation from Theta 1 Ori C in particular to trapezium stars to some extent. And so this plot here is showing you the measured flux of these detected cluster members in a submillimeter versus distance from Theta 1 Ori C. And you can see that there is a weak correlation here in the dust detections versus distance. But there's a pretty strong effect, which is that there are no massive disks within 0.03 parsecs. Which is what the EUV-dominated regime where we really expect very strong photoevaporation. And I will leave this here because I think Ryan is going to talk in a little bit about the gas properties, which we think might even be more strongly affected by photoevaporation. And then here's just a couple other things that are different in the ONC than other regions, presumably because of these environmental effects. You could look at the disk mass, stellar mass correlation. There seems to be a roughly linear correlation in most regions that have been studied. In the ONC, we don't really see that. We see more or less a flat line there when we look for that relationship. Another one is disk radius versus measured flux in the submillimeter. There's a pretty strong relationship measured in torus and rho OF. That's from work of Tripathi. This curve that I have plotted there, the dashed line shows the relation for those low mass isolated star forming regions. The ONC relation and all the data points, so that's the dotted line in the gray region. Again, not much of a correlation there. So presumably what's happening is these environmental effects in the ONC are erasing any intrinsic correlations that we see in these low density star forming regions. So that's something to be cautious about, given that these ONC-like regions are typical star forming regions and probably typical planet forming regions, and the relationships we infer when we look other places may not apply there.
Josh,
So this is my conclusion slide. I can stop right there. Thank you.
Perfect. Thank you for a very nice talk. And Wyden. All right. So Alvaro is asking if the disks are warmer in the ONC, would this affect not only the mass of the disk, but also the planetary masses that you form in them?
So the temperature effect that I was talking about was really just one of measurement. So we measure flux and we try to convert it into mass. And so if we've assumed the wrong temperature, then we'll get the wrong mass. So it affects that. Now, I think that question is also saying if the disks are hotter, what does that do to planet formation? And it does something there too, because if the material is hotter, if the disk is hotter, then the gravitational focusing is weaker, and so it's actually a little harder to build up bodies quickly. So it could have an effect there, but I wouldn't read too much into that because there's all these competing effects. For example, changing the dust to gas ratio, if you're photoevaporating the gas, that would enhance things like streaming instability or just gravitational instability because you can condense your solids to a thinner layer. So there's a lot of complicated competing effects that might be going on there.
We have another question from Gilberto Gomez. In addition to Alvaro's question, stellar density and well depth should add to disk truncation, right? Yes.
So that is true. Stellar density is another factor that one could try to examine and try to isolate from photoevaporation. Since we don't have a big sample of clusters to do that yet, we haven't really worried about it. And my understanding from the literature is that the photoevaporation is the dominant effect, but I would think flybys and dynamical truncation like that could be important as well.
And I have a very quick question, or we can continue later if we run out of time. but you showed the mass distribution of the disks is very different in Upper Scorpius and Lupus. Now, these environments are not that different. How could you explain this difference in mass distribution?
Yeah, Upper SCO is quite a bit older than Lupus. It's sort of 3 times older, so it's probably an age effect. It's just the mass is coagulated or dissipated, and we know that happens, right? The disk fraction decreases, the disk mass decreases with time. So that's probably what explains that.
Okay, great. Thank you again for a very
you.
nice talk and for taking the time. And we'll move on to the next speaker, which is Ryan. No, sorry. Just, here.
Right.
Okay, so we have.
Am I properly
circa,
audible to you guys on the other side of the stream? To the
Yes.
people in Leiden?
Yes, we hear you loud and clear. So this is
They can hear me?
circa
Okay, that's good.
Yes.
All right, so
Just a moment, let me introduce
thank you very
you.
much
One
for
second.
giving me the opportunity to give this talk here. Thank you also to Josh for giving a really nice introduction to the topic of disk masses in the OMC2. And am I okay? To the topic of disk masses in the OMC2 or in the Orion region as a whole. And so what I'll be talking about is not disks in the vicinity of the trapezium, which we saw just now, but rather disk masses in an environment that is a bit more isolated and sort of a backwater compared to the trapezium, which is the OMC2. And how observing those disks and comparing them to disks in other star-forming regions, comparing them to disks in the trapezium, can allow us to distinguish the influences of time and environment. So this was based on an article that we published in ANA just this summer, actually, together with Alvaro Akar and Levine van Dishoek. So if you have any further or more detailed questions, please either ask me for a copy or look up the paper, because I put the code up here. So to begin with talking about why we want to look at disks in different star-forming regions, if you look at Lupus and Orion, it becomes immediately obvious that even in the nearby universe, stars form under very, very different conditions indeed. If you look at Lupus, it's a fairly isolated environment. It's not as visually spectacular as Orion obviously is. But also in terms of the stars that are forming there, Lupus is basically without any really massive stars. The densities, the numbers of disks, there are very large differences. And as we saw previously, the environment of Orion is also quite extreme. The material there's feedback from the massive stars forming, so the interstellar material is heated. So a priori, there is not really much of a reason to assume that a disk that is formed in Lupus and a disk that is formed in Orion has the same properties. And so what we'll be trying today is try and figure out if we can observationally constrain this question. Are the initial properties of disks the same? And so what we'll be looking at in particular here is the easiest observable, although it has all kinds of complications, which is the continuum flux of disks and the dust mass that we infer from that. So what we know up to now from disk mass evolution, some of this, I'm afraid, partly overlaps the previous talk, is that if you look at an isolated low mass star forming region, it really seems that time evolution is the dominant factor in setting the distribution of disk masses. So if you look here, for instance, you see Lupus and Chameleon 1, which have roughly similar ages and roughly similar disk mass distributions. And then if you go to Upper SCO, which is older, around 6 to 10 megayears, you see that the disks lose a lot of their mass in that time. Now, this is a slightly simplified picture, but we'll get back to that later. And then in contrast, if you look at an environment like the trapezium cluster and the ONC, you see that there is, in this dense, massive star-forming region, something quite different going on with the disk masses. And so in particular, we seem to see evidence that photoevaporation actually matters a lot. And Josh Eisner, of course, talks about this. Rita Mann in 2014 also showed that if you get closer to the ionizing source in the trapezium, then your disk mass seems to drop quite rapidly indeed. And so this is usually blamed on the photoevaporation process. But this figure also raises the question, what happens if you go and look out here, in this environment, presumably the effects of the radiation of the star is much less important because it falls off as 1 over r squared. And so we want to know what happens to the disk masses in this environment. And this is where the OMC2 is very important because that's where it's located. So we do this. Obviously, we need to survey a large area, which is difficult, but fortunately, Alvaro Hacker's Orion 4D observations did cover a very large area of along the integral-shaped filaments, along along the integral-shaped filaments. So here you see the area in the vicinity of the trapezium, which is not fun to observe and very difficult with lots of residual emission. So we just don't look at it. And instead, we're interested in this region lying from a radius of 0.5 parsec away from the ionizing source. And so it's obvious if you look at this figure that there is a lot of large-scale structure in this data, which we're not interested in. So what we do is we use the fact that ALMA is an interferometer, and we can actually very easily filter it out. At the resolution of these observations, which were taken in band 3, we expect our disks to be unresolved. So this is actually a fairly simple thing that we can do. So we truncate our data. We observe only the more than 30 kilolepta baselines. And if you compare this region in red and this region in green, you can see that it actually seems to work very well. So these objects here, these point sources, are still clearly present, but a lot of the extended emission is now gone, which is exactly what we want. So just having the observations is not enough, because we also need to construct our disk mass distribution in an unbiased way. For that, it's very important that we don't bias ourselves too much to the mass of the disk, which is easily done. So what we do is we take a Spitzer selected sample based on Tom Baguette's 2012 Spitzer survey. And the nice thing of this is that it just doesn't just give us a large sample of disks. These are 137 disks in Orion. But it also actually allows us to observe some of the protostars, which are marked here as blue squares. And it also allows us to find some objects that do not seem to have counterparts in the Spitzer catalog, which will come in useful later. I'm afraid that for reasons of brevity, I will not be discussing the protostars too much. So I'll have to owe you that. And so if we zoom in a bit on this figure, this is only the disks showing both the non-detections and the detections. And you can see that indeed we do seem to have quite a few detections, and that they all do seem to correspond nicely to point spore sources in the KS image, which we used here from the division survey. And so here is our final sample of detections, as you can see, all unresolved or mostly unresolved. This one is on the edge. We have a total of 37 sources, which is about 35% of our sample. And if we superimpose them on the VISTA image, then we do see that, yeah, they all correspond nicely to these young stars. And we can do science with it. So as Josh just discussed, it isn't trivial going from continuum fluxes to disk masses. You need to make a lot of assumptions. And so one of the extra assumptions that we needed to make, because we're working in band 3, is that there might be some free contamination in these objects. So what we do here is we do estimate the expected amount of free emission, and we subtract that. And then we construct our disk mass distribution. Now we do this in the same way, using an average 20 Kelvin temperature, using a standard opacity, which at least will allow us in the next slide to compare this to other star forming regions where we made the same approximations. But we do want to know how robust this inferred disk mass distribution is. So we have tested two effects. The first is fairly simple, just increasing the temperature of these disks, and you can see that, yeah, there is an effect, but it's actually relatively small. It's around about 1 dex. The other assumption that we test is that there might be some completeness effects in our catalog. As I said before, we do observe a quite large sample of objects that are clearly point sources and quite bright millimeter wavelengths, but that do not seem to have counterparts in, that's a bit too far, that do not seem to have counterparts in the megathoton catalog. And so I got sources like this and this and this. Now, for some of these sources, we can actually find counterparts in other surveys. And the reason that they are not included in that catalog is that they are in fact very young sources, likely class 1s or class 0s, and so did not fit all the inclusion criteria. But there are some sources for which we find X-ray emission and actually counterparts, for instance, in the vision survey. And so we make the assumption that these sources are all disks. And this gives us a sort of an upper limit on on the effect of missing some sources, on the lack of completeness in the underlying Spitzer catalog. And so this is shown in the blue figure, Spitzer plus ALMA. And you can see also that here the effect is actually very small and only really starts to kick in above around 10 Earth masses in dust, which means that we actually have a quite good and quite complete catalog of disks. So this is the one figure that I hope you will be remembering from today, from this presentation at least, which is what happens when you compare this disk mass distribution that we've inferred from the OMC2 to different regions in other star-forming regions. So on the left panel, you see the OMC2 compared to low mass star-forming regions. And it's immediately obvious, both by eye and also if you do some statistics on it, that actually you cannot really distinguish between the OMC2 disks and Lupus and Chameleon, which are, as I said before, these sort of boring, quote unquote, low mass isolated environments with a probably quite similar age. Whereas on the other hand, if you compare the masses of OMC2 disks to disks in the trapezium, and this is Eisner's data again, then you can see that there is a very large difference. And it is a difference that you cannot just explain by giving them higher temperatures, because if anything, the trapezium disks should be even hotter and therefore have even lower masses than we see them as here. And so this is a remarkable result because, well, it has two implications. The first implication is that if OMC2 and Lupus look similar, then perhaps all disks that are formed in star-forming regions are formed with a similar disk mass distribution. And the only thing that makes the trapezium so low in mass is that it has been strongly photoevaporated for the past 1 million to 500,000 years. If that is true, then we can test that by comparing the disk mass distributions of these two regions. So the disk mass ratio from the OMC2 to the trapezium is around, it comes out to around 80% of mass that has been lost over the lifetime of these disks due to photoevaporation. And if you compare this to models of FUV photoevaporation in nearby star-forming regions, this actually works remarkably well. So we've compared this to both the fried grid and to the fairly simple semi-analytic solutions in Scully and Clark 2001. And both of those actually seem to match your observations rather well. And so we conclude that yes, in fact, in isolation, disk formation and evolution proceed similarly, and the cloud mass does not really matter for this. And yeah, photoevaporation really dominates the difference in these regions. So thank you very much for your attention. I'm very welcome to answer your questions.
Thank you, Sergey.
Sorry, let me turn my headset first and unmute the screen. There was a horrible echo when I had it in previously, so I hope that will work.
Yeah, so thank you again for your very nice talk. And we have no questions yet from our online audience. And I have a question. So you showed very nicely that the environment is not that important except for the extreme case of the ONC. Have you had a chance to look into binarity in any case?
Thank you for that question. No, I have not. Binarity is slightly difficult. One of the problems is that most of the other surveys that we've compared to, for instance, Lupus, does not seem to have a particularly high rate of binarity, and it's typically not included. It's certainly something I would like to include, but at this point, I'm afraid I can't give you a better answer to that. We'd probably need higher resolution observations for this as well.
Okay.
So thank you for your question.
Yeah, thank you. We have a question from Enrique. What is the ONC2 stellar population like, and does it look locally like a lower mass star forming region?
That's a very good question and very important. We don't have any indications that it does not look like what we expect, which is just a box standard IMF. Unfortunately, it is quite difficult to get accurate stellar age estimates for a region like the OMC2. People tend to focus a lot on the trapezium. But as was said previously, the assumption is usually that all of Orion has the same IMF, and that it is also similar to Lupus. Chameleon 1 probably is a bit bottom heavy, which might explain the lower mass that we observed there. Sorry, does this answer your question, Enrique? I see here, I mean whether there are local massive stars. No, there aren't really any.
Okay. Is there a local question there in Leiden?
Yes, there is.
Yeah. Okay. My question for you is how do you estimate the free emission, and what's the fractional contribution on the scales you imaged?
Yes. Thank you for the question. So what we do is admittedly fairly coarse because, again, this region is very large, and I think only a small fraction of it is covered with the VLA. So what we do instead is we used, this is Tichoniet's 2018, who measure, who do have free contribution of a quite large sample of class 2 and class 1 sources. So they, we used their estimates for the shape of the spectrum. And I am trying to remember now how large the contribution was. It is in the paper, and I can look it up for you in a moment. Tichoniet 2018. And so I think for this survey, for this sample, it comes out to, I think, maybe 10 to 20%. But it's important to note that we assume that it's the same for all of these sources. So it is very well possible that there are a few sources which have higher free contribution. We did check. There don't seem to be any droplets in there, so it should be fine. There are no objects that are really surrounded by an ionized envelope.
Okay. Thank you again for a very nice talk. We will be moving on to our next speaker, which is Orion Boyden.
Hello, can everyone hear me? Can you hear me?
Yeah, I hear you well. So Orion is from the University of Arizona, and he will be talking about protoplanetary disks cluster. Yeah, so yours.
All right. Hello, everybody. Greetings from Tucson, Arizona. So again, my name is Ryan. I'm a second-year grad student. Interesting results to the content. In my presentation, I'm going to focus on their gas. So our ALMA observations are the first to detect and resolve CO, HCl plus in over a dozen protoplanetary disks within the central motions of the ONC. For example, this is what we see at sub-millimeter wavelengths towards the well-known proplid 177341W. We see sub-millimeter dust, CO 3 to 2, and HCl plus 4 to 3 that is embedded within the bright ionization front that we have observed at optical wavelengths using HST over 20 years ago. Now, using these ALMA data, we measured the sizes of all of the line detections, and we've also constrained the underlying gas kinematics. And altogether, these measurements, they've enabled us to investigate just how molecular gas disk properties respond to a rich clustered environment such as the ONC. So before I get into these findings, I want to provide a recap of the ALMA program as described by Josh. So again, we mosaicked the entire central region of the ONC with ALMA at 850 microns. And the region that we observed is essentially what I'm showing on the right portion of this slide. And overall, our ALMA observations, they provide the deepest sensitivity and highest angular resolution of the central ONC region to date. And this has what has enabled us to detect and resolve a large number of disks in both dust and gas. So here's a continuum image of the ONC that is generated from our ALMA data. Again, very similar to what you saw in Josh's presentation. Here, the black triangle indicates the position of theta 1 OEC, the massive O star responsible for enhancing the photoionization within this region. Many of these tiny black dots that I'm showing in blue circles, these are spatially resolved disks that were detected and characterized in the continuum by Josh Eisner and collaborators. And as part of my work in grad school, I searched for line detections in the CO and HCO plus data cubes that were also generated from the ALMA observations, but are a little bit noisier. So I'm showing this continuum image instead. Now I specifically searched for CO and HCO plus detections towards the positions of the continuum sources that I'm showing here. And overall, I identified over a dozen CO and HCO plus detections, where here I'm using green circles to indicate where I detected CO and purple circles to indicate where I detected HCO plus. Now, both the dust and gas detections, they span a range of positions, as you can see here, as well as a range of distances from theta 1 OEC. And in total, we detected around 20 of the continuum sources in CO and around 10 in HCO plus. Here's what some of those gas detections look like when we zoom in towards their positions in the very massive data cubes that I have. So in each of these panels here, I'm showing moment 1 maps of gas plotted on top of contours of the continuum emission. So moment 1 maps kind of show the velocity, weight, and intensity of the gas, and therefore illustrate the underlying kinematics that we're seeing in the channel maps. The tracer being plotted is shown in the bottom right of each panel, and the name associated with each young stellar object, that's given in the top left. So what these moment 1 maps are showing us is that for many of the disks that we detect and resolve in the continuum, we're also seeing spatially and spectrally resolved gas with velocity gradients that are aligned with the dust major axes, as indicated by the change in color from blue to red that you're seeing in many of these panels. So this suggests that we detected rotating gas associated with the circumstellar disk. So in our analysis of these detections, we sort of had 2 approaches. First, we measured the sizes by fitting elliptico-Gaussians to the integrated emission map. Rather than, we're seeing that the C population is quite compact gas as well. So this figure here, similar to the setup figures in earlier slides, talks the cumulative distribution of gas radius generated for 2 different regions. So I show the CDF of gas radius for my ONC subs blue here, and then orange, I'm showing the CDF of generated from the subsample of gas disks that were detected in lupus and characterized by Megan Ansdell and collaborators. So here, gas size is computed as the same quantity for both of these 2 curves. So therefore, the plot is hinting at that whereas over half of the gas disks in lupus tend to have radii greater than, say, 200 AU, we're seeing no such gas radii in our ONC subsample. And this suggests that the high ionization environment of the Orion Nebula is also responsible for truncating gas sizes, which is a similar effect that has been found for the dust sizes by, again, Josh, whom you just heard from. So in addition to just, I guess, measuring the sizes and size distributions, we've also been investigating how the gas radius correlates with other physical properties. So in the left panel of this figure here, I'm plotting out gas radius versus dust radius for the entire ONC subsample. And I guess one thing that you'll notice in this left panel is that resolved the lupus subsample of gas, again by Megan collaborators. And for that lupus sample, the data are well described by a line with a slope of 2. So typically, in lupus, we find that the gas disks are twice as extended as the dust disks. However, ONC population detected, such a relationship does not really provide a reasonable fit to the data that I'm plotting. Rather, the best linear fits, which I'm showing as dashed purple lines, they actually suggest little to no correlation between gas radius and dust radius. So no correlation in this left panel, but however, we do see a strong positive correlation between the gas radius and distance from theta 1 ORC, which I'm showing in the right panel of this figure. Now in this right panel, the black dashed line, this is the best linear fit to the CO data, and the blue dashed line, this is the relationship between dust radius and distance from theta 1 ORC, which was again measured and constrained by Josh Eisner. Now, in here, in order to sort of facilitate a nicer comparison between the slopes obtained from the dust and gas data, I've standardized all of those measurements in this y-axis. Now, again, recall that the distance from theta 1 ORC is related to changes in the FUV radiation field strength. So therefore, these positive correlations that we're seeing here, they suggest that both the dust and gas radii are sensitive to changes in the and recall that the are larger than the dust sizes. This positive relation to us that the gas sizes, the disk, are more set to the external environment, photoionization, as opposed to driven processes. And finally, in my last slide here, this is the second thing that we've been doing in our analysis. So again, we believe we detected gas that's associated with rotating planetary disks. Since planetary disks are in near Keplerian rotation, well, then we developed a simple Keplerian model to fit to the channel maps in order to extract geometric disk parameters as well as pre-main sequence stellar masses. Here I'm showing such an example where we fit to the HCl plus channel maps of 181247, a well-known proplyid in the Orion Nebula. Typically, we found that our simple Keplerian model does a great job at fitting to the sources that we detected in HCl plus, a dense gas tracer. For the sources that we detected in optically thick CO, we typically found that we either need better data or a more sophisticated model in order to properly fit to those detections. And this is because, I guess for a large number of them, the CO detections, when we're fitting, we're finding that the models may often prefer fitting to the really often yields unrealistic disk parameters. So we don't like that. So a better data optically thin line, one way to get around that. Second, we are seeing some interesting topology differences between maps and models for some other CO sources. And typically, this is in a couple of channels, which turns out to be really important for a fitting as well. We think that some of these morphology differences are attributed to outflows or features from the externally driven winds that are known to be prominent in many of Orion's young stellar objects, but have yet to be fully characterized in terms of what they look like in synthetic CO or HCl plus channel maps. So those are sort of the next two steps in our analysis, obtaining better data and developing a more sophisticated radiative transfer model to include some of those possible non-disk structures. And yeah, that's everything I have for you today. I'll leave my takeaways on the slide. And I guess I have to zoom out for the questions, but here's some of my takeaways, and I'm happy to answer any questions that you have. So thank you.
So thank you, Brian, for a very interesting talk. We have a few questions for you. So I will start with the other speakers of our session. So Andrew Winter is asking if you've cross-matched the detections with the poplet sample to check for biases in your detected sample or radii.
Regarding a question?
Sorry, we lost you for a second. Did you hear the question?
I think the question was, as to whether some of the sources are related to the soul. And I guess the answer is yes. Many of the objects that we detected in gas have optically identified proplyds. Some of those are typically in that slide you saw with all the gas detections, the names that have those 6 numbers as opposed to some HC, then a few more numbers. Those are all proplyds. And luckily, in terms of how that might contaminate our observations, one way that it does is if the sources are dominated by free contamination in the continuum. And actually, the majority of the sources that I detected in gas have little to no free emission. Only a few of them do, and those are ones that I haven't done a lot of kinematic modeling on because they aren't detected over a sufficient spectral range. So I hope that answered your question. If not, I'm happy to talk with you later.
We have another question from Orion, and he's asking if you can derive a gas-to-dust ratio with your continuum and line data. And if so, is this consistent with the standard 1 to 100 value?
Well, our CO is 12 CO, which is optically thick. It'd be nicer to do that with 13 CO and C18O. So I haven't done that yet. And given the uncertainties with the dust mass, as Josh was talking, we might need to sort of get more data in sort of 2 avenues, both optically thin lines as well as maybe like a band 3 continuum mosaic as well to better measure the dust mass. So not yet, but that's a great idea.
Great. And one last question from Sirk, and he's asking about your explanation of what happens in the gas line fitting. Is how problematic the larger scale gas is for this?
Well, as hinted by the previous talk before me, all the residuals, it can get very messy, especially in our mosaic when we're closer to the BN and KL and OMC1 outflows. So when those are the cases, as I said, sometimes we'll get unrealistic like disk inclinations or gas radii where the best fit radii is much greater than the images that I'm fitting to, and that's just because all around there's really strong background CO emission. So cloud contamination is a problem in the CO. The HCO plus it's a little weaker in the background HCO plus overall, so it's not as problematic. But
okay. Right, now it's really one last question from Enrique.
Yeah.
You mentioned that some of the gas does not have disk signatures. Is it possible to think of it as infall onto the disk?
As infall onto the disk? Yeah, that's I sort of envision my the next 3 years of my PhD kind of exploring various different model scenarios, such as an infalling envelope, as well as the types of outflows that I mentioned. So it's something that I haven't really thought about yet and kind of need to do the radiative transfer modeling. But yeah, especially since these sources are relatively young as well. So
all right.
Great suggestion.
Well,
thank you.
Again
Yeah.
for a very good talk. And we'll move on to the next speaker of our session. And this is the last speaker, Andrew Winter from the University of Leicester. And Andrew will be talking to us about the solution to the proplyds lifetime problem.
Yeah, hi. So I'm gonna put forward, as I say, my ideas about the solution to the proplyd lifetime problem. So we've heard a lot about the disk properties in the Orion Nebula cluster, but we haven't really heard that much about proplyds. So I just want to cover what a proplyd is. So essentially, when a disk is close to a massive star, it can be heated by the FUV and the EUV photons, and you drive these outflows, which create this photodissociation region, and then what you're actually seeing as the proplyd is this bright ionization front here. So these are essentially driving rapid mass loss rates from these disks. One important thing to note is that even though these proplyds are the most impressive example of external photoevaporation is an extremely common process. It's not limited to this core region of the Orion Nebula cluster. So what I've done here, so this is a 2019 paper where we calculate the theoretical probability distribution function of stellar birth environments. So on the left here, we have the solar neighborhood and what we've got on the x-axis is just the density, the stellar density, and on the y-axis you have your FUV flux in units of g0. And these contours are just theoretical calculations of the lifetime of a disk evolving in that environment, using just a simple 1D viscous disk evolution model and the fried grid I had mentioned. And you can see the Orion Nebula Cluster sits at the very extreme ends of the FUV fluxes that are experienced in the local environments. But there are a huge number of regions which also experience strong FUV flux. So the Orion Nebula Cluster is really very important in understanding planet formation across a wide range of environments. If we go to something like the Central Molecular Zone, a region which might be more representative of where more planet formation occurred, sort of historically gas densities within a galactic disk were higher, then we see actually this is even more of a significant effect. We see even more external photoevaporation in higher densities. So really to understand protoplanetary disks in these really low density regions, sort of Taurus and Lupus, which are sitting down really at low FUV field strengths and low densities. And these are just not typical. If you want to understand planet formation of the majority of planets that we actually see, then you want to look at places like the Orion Nebula Cluster. But there's a problem, because there's a reason why external photoevaporation, I think, hasn't been focused on as much as it could have been, and it's because these propyds were discovered in the 90s, and they originally inferred very high mass loss rates for these propyds, so 10 to the minus 7, 10 to the minus 6 solar masses per year. But they also realized that 80% of disks remain in the Orion Nebula Cluster, despite the few million year average age of the stars. So there's something strange going on here. It's not clear what, and it seems to be, for a lot of people, it's sort of was evidence that maybe external photoevaporation wasn't as important as people thought. So I think it's been on a bit of a back burner, and there's been some suggestions as to what's actually going on in the Orion Nebula Cluster. Sauser and Hollenbach in 1999 suggested that these radial orbits of stars meant that they only spent a short period of time in the core, in the central regions, but modeling and theoretical destruction rates showed that this couldn't really be the case. This should always be dispersed on roughly 1 million year timescales. And even if this was the case, I mean, these mass loss rates are really implying that we're catching it at a very special time. It's kind of an uncomfortable coincidence. So how can we reconcile this with theory? Well, I just want to take a detour to revisit these sort of results from Josh Eisner et al. This flat disk mass host mass relationship is actually really a strange thing, because it's not consistent with any other region of a similar age. And not only that, though, but we heard that maybe photoevaporation was causing this strange relationship, but actually external photoevaporation should do the opposite, because you're in this environment of strong FUV fields. If you're a lower mass star, you have a smaller gravitational potential. That means your gravitational radius, the radius at which material can be efficiently photoevaporated, is smaller. So external photoevaporation should just deplete the disk down to lower radii and reduce the mass more rapidly. So you should get a steepening of the disk mass host mass relationship, not the other way around. So there's something really odd going on here. The other thing about the Orion Nebula Cluster, which has been known again since the 90s, is that there is a stellar age gradient. So your youngest stars preferentially occupy the center. Now, there's a huge range of different stellar ages that's been quoted for the Orion Nebula Cluster, but this gradient exists. And more recently, we've had a couple of papers claiming that there's actually multiple stellar populations that can be differentiated within the Orion Nebula Cluster. Whether or not they are multiple stellar populations, these studies also find, young stars close to the center, and there's been other studies that have found this as well. So we're beginning to unpick a bit about what might be going on here. The idea that I had to look at this was to model this multiple stellar populations, and in terms of just a simple n-body model, but with a gas potential that's consistent with the star formation going on over an extended period. So in this case, what you'd really expect is, because of the pressure gradient within a giant molecular cloud, you'd expect that the stars might form with a similar velocity dispersion perhaps to the gas, but because they no longer experience the pressure, they would form subvirially and begin to collapse towards the center as the gas is depleted. And because these stars might be collapsing inwards and undergoing dynamical encounters, as the gas is depleted, these older stars can migrate outwards. At the same time, you have these younger stars, these younger generations that are migrating inwards. So this is a natural way of explaining, say, mass segregation as well, because in order to get mass segregation in short periods of time, you want some sort of violent collapse process. And it's also a good way of obtaining this sort of stellar age gradient. So in these plots here, so in the left plot, we've just got time and then the half mass radius for the different stellar populations that I've denoted with different line styles and just different assumed star formation efficiencies. And we can see, depending on your star formation efficiency, you do get this age segregation. If we then self-consistently do the same calculations of the disk evolution, with the sort of the FUV flux, and we also take into account the extinction of the gas that's sat there in just a simple parametric way, we can actually reproduce pretty effectively the fraction of disks still surviving at the present day. So we've got this sort of, so the favored model is this 30% efficiency rate. And you can see the dashed line here is for the sort of core region of the Orion Nebula cluster, and the solid line is for the entire region. And this is sort of an observational estimate for the core, this dashed line here. So we get pretty decent disk fractions, pretty similar to what we've observed. So what does this reproduce in terms of the disk mass host mass relationship? Well, we can see because there's this young population that's young compared to the average stellar population, then you actually do see this contamination of the host mass disk mass relationship. So if we just take this as one big relationship, this black line, this solid black line here, this solid black line here is what you'd get if you just fitted naively a relationship to all of the stars that you see in the core. But then if you divide it up into the different populations, obviously this is a simplified model, but if you divide it all up into all the individual populations, you recover these disk mass host mass relationships, which are roughly linear or superlinear. In terms of disk mass. So rather than photoevaporation causing this, I think photoevaporation is still steepening the relationship, but you're getting this contamination just due to a young population of stars in the Orion Nebula cluster. And this works as well with the radius. Well, this is from the dust radii, again, from Josh Eisner's paper. You're looking at the sort of this quite flat relationship, but actually you should see something that's quite a lot steeper, just because photoevaporation can deplete a disk more efficiently if it's around a low mass star again. So just to also recount, just to briefly touch on the proplid properties and why this sort of misleading and why people should be careful when we're quoting certain values is actually we've reproduced quite a few examples of proplids that have ionization fronts which are extended in terms of ionization fronts which are very extended, more extended than the disk, and the brightnesses, the sort of surface brightnesses in H alpha that we detect are pretty, we get a number of cases where they reproduce the observed values, but the vast majority of cases of disks have brightnesses and radii below those which is detected. And this is just simply because the proplids that have been targeted are the brightest and the most extended. And that's very reasonable, but it does mean that when you come to talk about mass loss rates, really what you're getting from the proplids, which are the cases which the winds have been, the mass loss rates in the winds have been calculated, are really the tip of the iceberg in terms of the actual mass loss rates. The mass loss rates which are present throughout the Orion Nebula cluster or throughout the core are actually quite a lot lower. They're a few times 10 to the -8, and they're more consistent with the disk mass distributions that we see in the theory. So just to summarize the solution to the proplid lifetime problem, there's a lot of elements to this. The main thing that I want to hammer home is that there's probably a population of young stars with respect to the average age of the Orion Nebula cluster, and that really complicates any interpretation you want to have in terms of your disk properties. It means that the Orion Nebula cluster may not be the best place to look for signatures of external photoevaporation, and we really need to start looking at other regions as well to try and establish whether external photoevaporation is a significant effect on disk evolution. So yeah, just to summarize then, that really the main thing is that to be cautious about observational bias in disk samples, particularly in this case the proplids, but also actually in terms of looking at protoplanetary disks in general. The majority of disks, as I mentioned, form in these high density environments, and this is why these regions of high density which host this should be studied more. So thanks very much.
Thank you very much, Andrew. It was a very interesting talk. We have a question from Leiden. Dirk is asking how large are the core and full regions here?
Sorry, can you repeat that?
So I will also share the question.
Sorry, we got it here.
Yeah.
The core of the full the core of the Orion Nebula cluster is in the stellar core. Yeah. So it's about the same. So I had to use a Plummer sphere for numerical reasons because I wanted to estimate the gas potential. But the core I used the equivalent, so it's about 0.3 or 0.4 parsecs, something like that. The core radius. Yeah. So it's similar densities. The densities are very similar to what you get in the model.
We have another question from Josh. He asks that when you talk about steepening the disk mass-stellar mass relationships because of photoevaporation plus a variety of potential well depths, how general is that argument to solid versus gas?
Well, yeah, that's a big question. That's something that's being worked on by a lot of people. Basically, it depends on your grain size. So if you have small grains, then they can be entrained in the wind. So depending on the rate of grain growth, the age of the disks, it's a complicated answer. But yeah, it depends. If indeed the age of a lot of the disks in the core of the Orion Nebula cluster are young, then I guess you'd expect small grains. So this should be the case, but it could well be that this deviates at some age, and it's something that definitely needs to be investigated more.
We have another question from Odell. He's asking, is it fair to say that these results confirm the position taken multiple decades ago, that in Orion, the clearly most massive and hot stars formed recently, thus stopping star formation?
Yeah, so I know that Pavel Krupa has done a lot of work on this. I think that so basically the mechanism that I understand, which is quite promising for creating this multiple stellar populations sort of hypothesis, is that if you have a cluster of a certain mass within a certain mass range, it can create a small number of Orion Nebula, a small number of massive stars, and somewhere like the Orion Nebula cluster, because they form in pairs, they can actually be kicked out dynamically on short timescales of around 1 million years. So you get this, so you get a massive star forming, ionizing the medium, cutting off star formation, and then being kicked out by dynamical encounters, and then you can get a fresh phase of star formation going on. So yeah, I think that's what's been going on here, possibly.
Very good. I think we have one last question from Enrique. And he's saying that he agrees with Odell's suggestion according to what they see in their simulation. So this is a nice off-topic conversation that can be had later on. Well, thank you very much again for your talk, and thank all the end of the whole day as well. And look forward to seeing you for our next set of talks tomorrow. Thank you.